I was discussing the energy release rate, G, okay, the parameter, and you know that I told you that G was initially determined by Griffith, and he did many experiments on brittle material, that is glass, and he came out with a formulation that the energy release rate, okay. So that was in fact that is proportional to square of stress, okay, and multiplication of proportional to square of stress and crack length, and he found that pi sigma square A by E, okay, that is a constant which is a material property, and that material property he found it to be the surface energy, and then the sigma and root over A or root over pi A, pi anyway is constant, that it becomes also a material property. So that is called stress intensity factor, okay. And later, initially for infinite geometry with central crack, that geometry factor is 1, but for other finite geometries it will be different from 1. So we already know that concept of stress intensity factor. So instead of using the stress for design instead of the using the remote stress or stress value to calculate the or check the safety criteria or the crack will initiate or not, so stress intensity factor is used, and stress intensity factor and energy release rate, they are you can use interchangeably because they are the energy release rate G is proportional to K square, okay, by E dash, where E dash is E dash equal to Young's modulus for plane stress problems, and for plane strain problems it E divided by 1 minus nu square, where nu is Poisson's ratio. So we are discussing how to determine the G from experiment, okay. And yesterday I told you suppose this is a specimen with some crack length A, and if I am pulling it and fixing that certain displacement U, okay. So when I am pulling it up to U, so this is the load displacement curve, which is linearly elastic material, and then at U fixed, let us say crack gets propagated, so the load drops, okay. So and so that energy total energy release rate, potential energy, is the difference of strain energy and work done. And then during the process of crack growth, because load is that displacement is fixed displacement, so work done equal to 0. So to pi, that potential energy equal to strain energy, and then potential energy release rate is nothing but per unit area of crack advance. So thickness is B of the specimen. So when the crack advance, how much crack has propagated, the area is nothing but capital B into delta A. So G becomes the area OAB, okay, divided by B delta A. This is for fixed drift, that means when U is fixed. Now for suppose you put a dead load, okay, that means load is fixed. You put a dead load on this specimen. Suppose you just make the other way, this from the top you fix in a pin, and in bottom you put a load, okay. Okay, so here, so when you put the load, so it initially that is load displacement called linear ratio up to point A, O to A, then here crack growth occurs, okay. So A to B, so that is when there is crack growth delta A, so the points, because you have fixed, load is fixed, load cannot be changed, so it moves from A to B, okay, and A to B, then there is additional displacement U2, okay, and this is when the crack length A plus delta A. Now if you have to calculate how much, what is the energy release rate for this dead that is called load control condition when load is fixed, so or for a given dead load. So here also same, the potential energy equal to UE minus W. Now here U is the change in strain energy, which is the area under load displacement curve. So half P P into U2 minus half P into U1. Okay, but P, because P is fixed, so that is the change strain energy. And how much is the work done? Work done is in terms of P dx integral. So P and dx means delta P du integral. U is the displacement. So P is fixed. So du integral is from U1 to U2. So U2 minus U1. Okay. So delta U and this is delta W. And if you substitute it in pi, so you will get, and then divided by area is B into delta A. So you get G energy related to 1 by B delta A, half P into E2 minus E1. And if you see in terms of geometry, there is nothing but same thing, 1 by B, the area OAB divided by delta A. So if you see here also, this area OAB divided by delta A, okay, when that is point is moved from A to B, and here also when point is moved from A to B, this is the area, AOB. So expression remains same, but if you see the area will be different. But here you see when the displacement is fixed, and other cases the load is fixed. Okay, so in load release conditions, area you can say that additional area. So that additional energy, which is because of the during the motion or during the crack growth, there are some work also is done on the specimen, but the expression for G, it remains same. Okay, so this gives the method a experimental method to determine the G, that is strain energy release rate, sorry, that is potential energy release rate, which is nothing but crack tip parameter. That means you can also so GC is critical value, okay, for crack to initiate. Then if G is less than GC, then your crack will not initiate for a given loading condition, and if G is greater than GC, then you can say that crack will initiate or propagate. And this is valid for brittle materials having behavior a linear elastic, which behave in a linear elastic manner. Okay, and from G also you can calculate expression of K, because G equal to mod 1 K, that is K1 square by E for plane stress condition, and K1 square by E dash for plane strain condition. So this gives you a method not only for determination of G parameter, also determination of the K1, that is the mode 1 stress intensity factor. There is another method. It is slightly so here we are using the area under the curve during the crack propagation. This method G in terms of compliance is nothing but inverse of stiffness. So we have load displacement curve. So this slope is called stiffness K, and the other slope is called compliance. Okay, slope. The compliance is nothing 1 by K, inverse of stiffness. So you know that when the crack, suppose here this is load displacement curve. So if the crack is length A, and suppose you are pulling it, then you have a higher stiffness. Okay, because and if the crack property A plus delta A, then stiffness becomes lower. Okay, because the material that is the stiffness of the system depends upon what is the remaining ligament or area. So higher crack means it is a lesser stiffness and more compliance. So by knowing the change in compliance, it means when the crack is growing from A plus delta A, the compliance also increases, stiffness decreases, compliance increases. So by changing, knowing how compliance value change from during crack growth, we can also find G. So that is called the method of compliance. So as I told, the stiffness is P by U, so the compliance will become U by P. Actually it is del U by del P, but for a linear elastic material you can take it as also U by P, because it is just a straight line, the slope is fixed. Now for fixed grip condition, so the change in the strain energy is nothing but strain energy. So here the fixed grip condition, if you see the earlier same slide is that means initially you pull it up to U, then you fix it, so then because of crack growth it is decreasing, the load decreases. Okay, so the change in strain energy at the condition A plus dA minus strain energy at the condition A, and strain energy here is P plus delta P into U by 2. So here the delta P is actually negative. Okay, so this is just symbol. Okay, don't confuse about the value. It is delta P here. When the crack increases, delta P will reduce, and that is negative. So the delta change in strain energy nothing but half into dP into U, and the G value is nothing, and for W, for fixed grip condition, delta D equal to 0. You know that already. You have calculated. We have already discussed that in earlier slide. So G equal to potential D potential pi by dA, negative d pi by dA. So this becomes d W by minus d del U strain energy divided by dA, and dA equal to B into dA, small dA, that is crack increase in crack length. This dW equal to 0 for fixed grip. So if you substitute this dUE, the change in strain energy, so you get minus 1 by 2B U dP by dA, because this dA term will come here on the denominator, and this dP by dA we write in terms of compliance. So we know that compliance equals U by P, or P I can write equal to U by compliance. So when I am differentiating P with respect to small a, so and then I want to find, so what is changing? U is not changing because it is fixed grip condition. U is fixed, so changing is what is changing is compliance. So when I differentiate P with respect to A, that crack length, that means I am differentiating. So U, the term P equal to U by C, so U comes out because it is not a function of crack length. Then dP by it becomes U into 1 by C square dC by dA. Okay, it is simply and minus sign, minus 1 by c square dc by dA, and minus minus cancels. So I get 1 by 2b. Then already u was there, another u comes from this dp by dA. So u square by c square dc by dA. So, and u by c is nothing but p. So this square becomes p square. So it becomes p square by 2b into dc by dA. So what essentially I am telling, that if you have done this experiment and you know the how much slope change, that compliance changes with crack length, so you can calculate dc by dA this quantity, then multiply by p square divided by 2b, you will get the g, strain energy, that is the potential energy release rate, g parameter. Okay, and of course dA has to be tends to 0, because you know, when that dA the crack length becomes higher, so this is all the limit delta A tends to 0. Okay, so this is a and we'll see an example where we can use this method to calculate g and also k, because g and k are related. Similarly for fixed load condition, okay, so everywhere we will be discussing this fixed drift and fixed load condition. Okay, to make it more clear, so fixed load condition, you know that p is fixed. So when the crack length changes plus the delta A, the slope that is decreases, that is stiffness decreases, for compliance increases. So here also we will use same expression, g equal to dw minus d strain energy by dA, and here dw is nothing but p, that load is fixed, into du, and u is as in the previous case is a half p du, and if you substitute in the expression g, I get 1 by 2b load into del u by dA, and here now substitute u equal to p into c, and p is fixed here because fixed load, p is constant, so p comes out, so p into p becomes p square. What remains is the dc by dA. So the expression g here also p square by 2d dc by dA. So you can see, irrespective of whether previous case also is p square by 2d dc by dA. So whether it is a fixed load or fixed displacement, that is fixed drift, the expression remains same. So here also the compliance, if you know how much it is changing, you can calculate the energy release rate. Okay. So it is a summary for fixed drift. It is nothing but 1 by 2b u square by c square dc by dA, which is also written, can be written as 1 by 2b p square dc by dA. For fixed load condition, it is 1 by 2b p square dc by dA. So strain release rate is identical for fixed and fixed load. So this is proportional to the, what I am saying, strain release rate, that is the actually it is potential energy release rate. Okay, g is called potential energy release rate. It is proportional to the dc by dA. Okay, so for certain geometry, suppose dc by dA higher. Okay, that means compliance changes very quickly. Then in that case g will be higher, that is potential energy rate will be higher. Okay, so what you can do, you can also, this also it is gives a method to evaluate also numerically. For example, you cannot do experiment in certain geometries. For example, suppose there is a big vessel, lesser vessel, or certain component, you cannot do the experiment. You cannot make a crack, and you cannot do experiment. It is not possible. You can do experiment only on small specimen. Okay, but our aim is to evaluate the g parameter or stress index factor for actual real life component. So in that case, what you will do? This method will let us see. You can do a numerical simulation, okay, using finite element method or the method. So in numerical simulation, you make a crack, okay, then you calculate what is the stiffness. That means you apply load and you get the displacement, or you apply displacement and get a load. So from that you can calculate the stiffness of the structure, okay, stiffness of the component. Then you make another crack of slightly increase the crack, a plus delta A, and you calculate how much the stiffness, and if you increase the crack, stiffness will be reduced or compliance will increase. And that change in compliance, okay, with respect to delta A, that will give you dc by dA. And for a given load, so you can always calculate the potential energy release rate, and then you can convert it to stress intensity factor. Okay, so the g is proportional to p square. So and g is proportional to k square. It is k square by e. K is stress intensity factor, that is mode 1 stress intensity factor. So k will be always proportional to the load. Okay, so this expression, the handbook expression, if you see in the previous class, Ranjit must have shown you the handbook.